Now I'm going to talk to you a little bit about Leo. Inside, we have written many things, really specifically toward application to the turbomachinery flow problem. Now, some of them pretty straightforward and simple, such as inlet profile, excess static pressure profile, radial equilibrium conditions at the exit, and a little bit more advanced capability called non-reflective boundary conditions for both upstream and downstream. And that not only for one passage, if implemented, can be applied to a number of passages. All right. We also have a model available for cavity flow. We also have a capability to introduce actually this model to mimic the effect due to stage or other flow features in a turbomachinery environment. We do multi-stage steady flow calculation using mixing plan, and we mix all the five primary quantities such as mass conservation, three-component momentum conservation, and the energy conservation in a circumferentially every sense across the mixing plan. Okay, that's the mixing plan model used for steady multi-stage simulation. For instantly flow simulation, we have two models available. One is the standard called sliding boundary methods using interpolation between a stationary mesh and rotating mesh. This is pretty standard procedures. Okay, and the other capability is a frozen rotor model. That is one under one major assumptions. That assumption is that rotating speed compared with the through flow speed, so there's a large ratio. So it's not recommended. If you do time accurate simulation, you better using sliding boundary conditions. And frozen rotor allows you to apply that for the steady multi-stage too. Okay, somehow allowed you to let flow go through reverse. But this is a stopgap measure of the capability. So our recommendation of using this steady multi-stage is mixing plan, or anti-steady simulation is sliding boundary conditions. The code also written allowed you to introduce cooling air, film cooling air, and there's also a lot of routine in the code to give you enough feedback how this turbomachinery actually perform, such as inlet total pressure, exit total pressure, temperature, as a function iteration. There's many information, both in terms of one-dimensional, what we call mainline information, or we call streamline type of information. And then we also dump out the restart file allows you to see three-dimensional flow field. Okay. The last one is, listed here, is 2D simulation with high ratio, because people really interested in want to design it for you. Current design starting procedure is design two-dimensional sections, and we have a very efficient, fast method to do 2D simulations. Only use two slides, single elements across in the spanwise directions.